pen isn't showing it. Okay, nice. So we know Coulomb's law, right? What does it states? Hmm? Like if you have two charges, say this is some space, this is some region, wherein you have two charges, 2 point charges, in particular 2 point charges. Okay, this is charge number one
Yes.
Q, and this is charge number two Q2. Who came now? Someone wants to join the call. How can I admit her? Okay. So these are two charges, and the separation between them is smaller. Coulomb law states that the force between them is directly proportional to product of the charges. Okay, and the force is inversely proportional to the square of distance between them. Right? We have studied this thing, and we combine both of them. So it looks like this: F is directly proportional to Q1 Q2 over R square. From here, what we can infer is F is equal to some constant times Q1 Q2 over R square, right? This is the result. Uh, does everybody agree with me on this expression that we have arrived? This thing? Yes or no, people? Please reply. So what does this give you? This gives you force between 2 point charges. It gives you force between 2 point charges. So have you studied properties of charges? Is it completed? Now talking about this K, this space is vacuum here. This thing, you do not have anything in this region. This is vacuum. Vacuum means absence of anything. Like we also term it as free space. You do not have any charge or something in it. People, please reply. Have you completed properties of charges, or should I start with the beginning of the chapter? Everybody, please tell me. Do you know the properties of charges, the unit, their nature, conservation of charges, quantization of charges, amount of charge on an electron? Is this thing completed or not? Please, if you aren't able to turn on your mic, you can type it in the chat box. Hello, can everybody hear me? Is everybody there or not? Or just you have joined the meeting, or you are only
Huh.
Soyajaksh, what is your name? Is
Okay.
replying.
Ritual.
So, should I
Completed.
start? Completed. Everything before the Coulomb's law is completed, right?
Yes, sir.
Have you studied? Please stay on the line. Have you studied this about permittivity of free space, permittivity of medium, and all relative permittivity? Have you done that?
Yes, sir.
No. Some people are giving a thumbs down. Permittivity is not done.
Um, One
So we
second.
can study permittivity, if you, and then we can move on to electric field. Okay,
Okay.
so this expression, everybody look carefully over this expression. You have, you might have seen this kind of expression in your 11th standard also in gravitation chapter, right? Wherein
Yes.
the charges, instead of charges you
Mass.
have mass, and instead of this k you had capital G. Now talking about this equation, this expression what we have written, F is equal to k q1 q2 over r square. K is what? K is your constant. If anyone doesn't get what I am saying, please tell me, because I am on a different tab. Like, I'm not in Google Meet, I am on this board. So if
Okay.
you will be messaging me, I might not get the message. So if you want me to repeat or want to notify anything about, so just turn on your mic and tell me. So this k is a constant. Later also we will talk why there is a need to bring these constant, because here we wrote f is directly proportional to q1 q2, f is inversely proportional to r square, then we wrote it together all of them. Then after removing this proportionality sign we bring in a k. Later on in the last 5 minutes, or maybe after the class 5 minutes, we will discuss why we bring k here. Okay, so let us just talk in terms of physics now. So right now this k is your constant, and majorly this k is not written as k, it is written like this: 1 over 4 pi epsilon 0 q1 q2 over r square. Okay, so this thing is a square, please don't mind the writing. This is same as the above wala equation, but the only difference is instead of k we have written symbol's name is epsilon. Symbol name is epsilon. This thing is called epsilon. It is a symbol. Okay, and this is, since you have put it a zero, free space means the region in which where your charges are kept, you do not have any gas or any other molecule in their vicinity.
Una
Meaning in this
copeta.
box there are only two charges, q1 and q2, and this arrow represents the distance between them. Other than these two charges, you do not have anything, meaning it is vacuum, free space. Okay, so we have written this equation for vacuum or free space. Therefore, we have taken a zero here. Can you see my cursor? We have taken a zero here with epsilon, and we will call it as epsilon naught or epsilon zero. And this permittivity is permittivity of free space or vacuum. Now let us just talk about it. Why permittivity? Now, right now I am talking to you. Okay, you might be hearing my fan's voice, which is running over my head, but you can hear my voice. Now, instead of in this room, wind starts to blow, too much wind is blowing, you will not be able to hear me, right? Meaning, the medium in which I am sitting right now is allowing me to speak, and my voice can hear you, can reach you, and you can hear me. The medium is allowing me, like it is permitting me. Therefore, it is the term permittivity. Now, in this region, let us draw the diagram again. This diagram is like a little bit of messy. So this is a box, say. Inside this box, you do not have anything. You only have two charges. This is a charge. Its name is Q1. This is another charge. Its name is Q2. And this is the line joining them. Now, Q1 will attract or repel Q2 depending upon what their nature is. You might have studied in the previous classes. If they are unlike, they will attract each other, and if they are of same nature, meaning they are like positive positive or negative negative. then they will repel each other. Suppose one of them is positive and one of them is negative. So what will happen? Say this is positive, for instance, only we are assuming that, and this is negative. So Q1 will get attracted by Q2 along this line, and Q2 will get attracted by Q1 along this line. Now you do not have anything in their vicinity. This medium is allowing these two charges to come together. Okay. Uh,
Okay.
whose mic is on, please turn it off. Like some noise is coming. Later on, if you want to tell anything, you can turn it on again. Okay. So right now, this medium is allowing the force to act. Now, instead of this medium, if I put these charges in something, like I fill water and put the charges in that water. Say right now, we will calculate force in medium. Force between two charges in a medium. Now this is some region. Suppose in this region water is filled. This is your charge Q1. I'm writing the name a little bit above, and this is your charge Q2. Okay. Now suppose water or some other molecule is there, maybe HCl, or I do not know, like there is some molecule, but whatever molecule it is, it has two charges. Suppose if you have water, water is like this, H plus, OH minus. HCl is also like this, H plus, Cl minus, meaning this molecule also have some positive and negative charge. So we will denote them like this with a ellipse like structure, one positive, one negative. Okay, let me just zoom it a little bit so you can clearly see the picture. So this is the situation right now. You have two charges, and the you have something in suppose say water, assume water. Okay, so what will happen? There are water molecules everywhere. If this Q1 is positive, if this thing is positive, what will happen? All the water molecules will come close to Q1 with the negative here and positive here. Another water molecule will come here with the negative here and positive here, and this thing will keep on repeating, right? I hope everybody is getting what I am trying to say. Meaning this, the middle wala charge, this charge will get surrounded by the water molecules. This charge I am talking about, this one. We just color it. This is the original charge. This charge will get surrounded by the molecules of the medium. Similarly, this charge will also get surrounded by the molecules of the medium. If say this charge is positive, again same thing will happen. The negative will be here and the positive will be here. And there will be another molecule, negative here, positive here, negative here, positive here. Same way here also. Meaning everywhere in its vicinity, everywhere close to the molecule, it will get surrounded by the medium ka molecules. Okay, now this charge cannot exert force on this charge, meaning it can exert, but the force will not be as effective as in the previous case, because in the previous case you did not have anything in between. Where did it go? Here you can see everything was empty, nothing was there. Here there are charges, so the charges will surround the original charges, and the force is there, but the medium is not allowing the force. Are you getting? It is same as I am speaking, but some DJ is turned on here, and you cannot hear my voice. Why? Because why? Whatever I am speaking, the DJ is creating much more sound than that. So my sound is negligible as compared to that. Same is happening here. The charges are exerting force on each other. Q1 is applying force on Q2, but the surrounding molecules have surrounded the original charge, and it is like shielding. You might have studied in chemistry. Okay, so please don't send this weird emojis. Let us just study seriously. Just give a thumbs up. uh, okay, so whatever I am trying to say is your force will reduce, meaning the force in medium If I try to write the force in medium, will be less than the force in vacuum. Okay, why? Because the charges got surrounded by the medium ka molecules. So how I can write the force of vacuum like this? K Q1 Q2 divided by R square. Okay, or I can write it like this. Now suppose this is the force of the vacuum. I want to write it for medium, and I want it to be less than this particular thing. What should I do? If I divide this with something, the overall value will go down, right? Okay, are you getting what I'm trying to say? If I divide this vacuum force with some number, the overall force will get reduced, right? This I can write it like this also. 1 by 4 pi epsilon 0 q1 q2 upon r square. This is the force in vacuum. I want to write the force in medium, and what I know is the force is medium is less than this particular force. So somehow I have to write an equation wherein all these terms should be present. One. Second point, these terms, the value should get reduced. So to do so, I will divide this equation by something. Meaning, if I write it like this, force of medium is 1 by 4 pi epsilon 0, then you have q1 q2 by r square, and we are going to divide this thing with a number capital K. Okay, what is capital K? Capital K is called dielectric constant. Later on we will study dielectrics when we will study capacitor and all. So your capital K is called dielectric constant, and this capital K's value is always greater than 1. Its value is always greater than 1, meaning this entire thing is being divided by a number greater than 1. What happens when you divide anything by a number greater than 1? The overall number gets reduced. So if you pay attention to it, what I have written here, I have written nothing. I have just written F medium, like your force in medium is equal to force in vacuum divided by the capital K. Yes or no, people? Did you get this thing? Your force in medium gets reduced. How much times? K times. What is K? Dielectric constant of this particular medium in which your charges are kept. So if you bring your charges in some medium, your force will get reduced. By what amount? By this K ka amount. This K. What is this K? This K is dependent on medium. Like for water, it is 80. So if you calculate force in vacuum for water, you will have a 80 in the denominator. And if you calculate the force for two charges in vacuum, you will not have the 80 in the denominator. So when you get 80 in the denominator, for sure your force is going to get reduced, right? Yes or no? So this K gives you the measure by how much amount your force is going to get reduced. I hope everybody is comfortable with this thing. And if it was taught in your previous class, please let me know. We will directly go on to electric fields. Otherwise, we will continue from here. So we will come one step below. Everybody is understanding, right? Please let me know if you are not getting, and please let me know if I am going too fast. We'll reduce the pace. The main motive is to get a hold of everything. Okay, so let us just continue. Now this thing can be written as like this also. Did the pen go? Okay, this thing can be written as like this. Now F medium, it can be written as like this: 1 by 4 pi. It is epsilon naught into k. Instead of epsilon naught into k, instead of writing two terms, I'm just going to write epsilon. Just epsilon, no zero with the epsilon. Okay, then the usual thing, q1 q2 over r square. So what does epsilon means? Epsilon is nothing but epsilon 0 into k. And what is the name of this epsilon? We know the name of your previous epsilon was permittivity of free space, right? We did it here. This epsilon 0 was permittivity of free space. Let me just close this thing. This epsilon 0 was permittivity of free space. Free space means vacuum. Right now, we don't have vacuum. We have some medium. So we will write the name as permittivity of medium. So this epsilon is nothing but permittivity of medium. It's looking like H T T. So I hope everybody is getting what I am trying to say. In medium, your force gets reduced by what number? By K. What is K? K is called dielectric constant. What is the value? Value is always greater than 1. It depends on different things. It depends on the type of medium. For water, it is 80, meaning in vacuum the force will be F, but in water the force will be F divided by 80, meaning it will get reduced by 80 times. So the way we write it is with epsilon naught you need to write a K, or either you can write it like this: epsilon naught into K is just epsilon. One more way is there to write it. Instead of K you can write ER. So should, like, whenever you see it in some book, you should not feel that you have not learned it. So instead of this K, I will write epsilon R. This is your constant, 1 by 4 pi epsilon R. Epsilon 0 epsilon R. Instead of this K, I am going to write epsilon R. And again we'll write the charges and all, q1 q2 by r square. Okay, and these are same only, epsilon 0 epsilon r, meaning your K and epsilon r are one and the same only. What is this epsilon r? It is called relative permittivity. This thing is called relative permittivity. Why relative permittivity? We'll see in a moment. I hate this tabs and all. The writing is like really slow and comes very much weird. So I hope you can understand it. I'm trying to write it as neatly as possible. So this is K, this is epsilon r. Let me just put a line over here. So these are the I am doing expressions here, like you are sitting in front of me. Okay. So let me just change the pen color. Okay. So this left hand side is the theory part, and this right hand side is the naming part. Okay. Where is the mouse? So if you look here, these terms, you will observe I am want you to look here. If you want to write K, K is epsilon over epsilon 0. Right? Epsilon over epsilon naught. Both of them, this K and this ER, both of them are ratios of same quantity, meaning they are unitless. Why unitless? Because these are just ratios. Who came right now? Right? Someone wants to join this call. The name is not there. Dot. Okay, so how many people are there in the meeting right now with us? 7, including, like, excluding me. 1, 2, 3, 4, 5. So 2 tabs are of me. and you people are 5. Okay, nice. So let us just continue. We what we studied till now is we started with Coulomb's law, basic, you know Coulomb's law. We wrote the equation, and then we studied about what is going to happen if you bring your charges into the medium, and we discussed that the force in the medium is going to be less than the force in vacuum. Then we wrote the force in vacuum, and we discussed that we want this force to be less. So how can this force be less? So we divided this entire force by a number called capital K. Please do not confuse. This is just a K, for you can write C also instead of this K, this one K, because it is just a symbol of this thing, 1 by 4 by epsilon 0. This K here is just the symbol for this thing, 1 by 4 by epsilon 0. But this K, the K with which you are dividing, is in itself a quantity which is called dielectric constant, and its value is greater than 1. So if you divide it with the dielectric constant, your force is going to get reduced. Then instead of this epsilon naught K, we just wrote epsilon, or instead of this K, we wrote epsilon R. So I have written the names here. Now what I want you to know is, you might be knowing previously only, this epsilon have some value. So if you want to write epsilon, you can write it like this from this equation. If you want to write epsilon, it will be written as like this. So F R square divided by Q1 Q2 is equal to this entire thing. And what is this entire thing? This entire thing is your K, right? So K will be this thing. Its value is 9 into 10 raised to 9, and the unit will be Newton meter square per Coulomb square. Let me just erase this line. Its unit will be, you can see, this is Newton distance square Coulomb square. So Newton meter square per Coulomb square. Now if you want, you can just find the value of epsilon also. So you need to again rearrange the equation. It will be epsilon 0. I am just rearranging the equation, not doing anything fancy. Epsilon will go up, everything will come here, and q1 q2 will be in the numerator. So q1 q2, observe it carefully. Q1 comes here, q2 comes here. Force will come down, radius square, sorry, distance square will come down. Force, distance square, and you have a 4 pi. So on calculating, you will get it as 8.83, if I am not wrong, into 10 raised to minus 11. The value might be different. I've not memorized it, and there is no need for you also to memorize it. It will be given in the exam, any of them. So these are just the values, and this is it. This is the first part of the lesson, the introductory part of your electrostatics. You cannot read anything. Okay, so right now we will move to electric fields. We'll see what is electric field and why there is a need to study electric field and all. If you observe, always writing the Coulomb's law, you need two charges, right? You cannot write Coulomb's law for three charges, four charges. Okay, every time you will be requiring two charges to write the Coulomb's law. It will give you force between the two charges. And then you have superposition principle. We will look at that later, like we can calculate force between two charges and add them. Right now we'll move on to electric field. Now electric field is defined for a single charge. So we will give a name to a charge as point charge. Okay. So you have two charges placed in vacuum. Yes. These are your two charges. One charge's name is capital Q, and the other one is small q, and this is the line connecting them, and this distance between them is say small r. Now what will happen, q1, this capital Q will repel this charge, suppose they are of positive nature. Capital Q will repel small q. On the same time, small q will also repel capital Q. Does everybody agree with me on this? Both of the charges will repel each other. Now, when you are in air, like an aeroplane is
No,
flying, the
no,
earth is attracting the aeroplane. At the same time, the
ये
aeroplane is
didn't
also
work out.
attracting the earth. But the earth do not come towards the
Hello.
aeroplane, but the aeroplane do come towards the earth.
हाँ,
This is because the mass of the earth is too much.
ये
The
didn't work
inertia
out.
of the earth is too much. It does not get shifted. There is like the
हाँ,
plane is not able to attract the earth. Why? Because
Bengala.
the mass of the earth is way too much as compared to the aeroplane, and the aeroplane mass is very less as compared to the earth. Same thing we are going to do here. What we are going to do here is we are going to make this charge small q as a test charge, and we will write a zero here, small zero. Zero means q0 is a test charge. Test charge means a charge so small in magnitude that it can only experience the force. It is so small that it cannot attract or repel the other charges. Why? Because it is very small. It can only experience the force, like a very seedha sada insan. Everybody can shout over him and he will not utter a word. So this q naught is the test charge, and its value is so small that it will not attract the capital Q, neither it can repel the capital Q. So we can just write about test charge. Charge so small in magnitude such that it cannot exert forces on other charges. So this is about your test charge. If you want, you can write it somewhere in your book. Okay, getting my point? So if we write the Coulomb's law for them, it will be like this. F is equal to, I'm not writing the entire 1 by 4 by epsilon thing. I'm just writing small k. This small k means 1 by 4 by epsilon 0. You are smart people, you can understand. Okay, so this will be charge 1, which is capital Q, another charge, which is small q, divided by distance square. Now, this q naught is very small, right? If I divide this entire thing by q naught, what will happen? It will look like this. F upon q naught is equal to k capital Q small q r square upon q naught. So this q naught will get cancelled. What am I going to get in the next equation? I will get like this. F by q naught is equal to k q divided by r square. This thing is nothing but your electric field, and it is force experienced by a charge per unit test charge. What you have to do, you have to divide the force ka equation with the other charge. Now this thing, if you write it this thing, E is equal to k q over r square, or you can write it like this also. Instead of k, you can write 1 by 4 pi epsilon 0 q by r square. What terms are there in this equation? You have capital Q, you have distance. Other than that, this entire thing is constant. So this term this equation is the electric field of the charge q at a distance r. If somebody asks you, you have a charge whose name is capital Q, what is going to be the electric field of this capital Q at a distance r? Say this is point P. This point is P. Like I am just giving name to this point P. If someone asks you what is the electric field at point P, so you should tell that person it is going to be K Q divided by R square. This is going to be my electric field at this point. If the distance will change, the value of the electric field will change. Easy. It is nothing. You want to find electric field. Kiska electric field? This charges electric field. Where? Here. R distance away. So just it will be going to be K charge ka value divided by distance square. It is same as Coulomb's law only. The only thing is in Coulomb's law you have two charges. In electric field you have only one charge. In electric field you have only one charge. Is it same as the electric field? So this is the electric field due to a point charge. So let me just write electric field due to a point charge, and let us just write the definition of electric field also. It is force experienced by a charge per unit test charge. There might be other definitions in the book, but this fits quite well. And let me just write the symbol of electric field also. The symbol of electric field is E with a bar over it, meaning your electric field is coming from force, right? So if force is a vector, electric field should also be a vector. We will write all of that below. So electric field E vector is force experienced by a charge per unit test charge, or somewhere it is written electric field is space surrounding a charge in which electrical behavior can be observed. It's called electric field. We can write that also. Space or region surrounding a charge in which electrical effects can be observed is called electric field. Space surrounding a charge in which electrical behavior can be observed is called electric field. Is it clear, everybody? We'll get further clarity. Like we will find electric field due to one charge, due to two charges, due to ring, due to some sphere, due to some sheet, due to some wire, everything. Like as we move on further, the things will repeat and you will get further clarity. So space surrounding a charge in which electrical behavior can be observed is called electric field. Please don't mind the writing. It is not very much nice, but you can read it. The symbol is E vector. Okay, so this electric field is a vector quantity. So your E is a vector quantity. And it is given like this. E vector is force vector divided by Q0. Okay, and then its unit should be what? Can anybody tell me its unit? SI unit, please. Someone tell me. Its SI unit is going to be what? What is force ka unit, people?
Newton,
Newton. And what is charge ka unit? Coulomb. So its
Coulomb.
SI unit is going to be Newton per capital C. Newton per Coulomb, or you can write it like this: Newton Coulomb C raised to minus 1. So this is about electric field. And you are CBSE board. We will read the textbook also. so that you get simultaneously, it should be linked, like you should know where it is there in your textbook also. So every class whatever we have studied, we will look at that into the textbook also. So this is your electric field. Let us just move further and try to write electric field ka formula for a charge. So let me just draw a line. Okay, if someone wants going to repeat anything, please let me know, and we will be studying at your pace. What did happen? Did someone came in the meeting? No. Okay. So we'll write E bar. E bar means electric field. We'll use symbols. Is somebody trying to say something? Raising hand or something? Tudung tudung voice is coming. No messages. Okay. What happened? Please tell. I think it is by mistake. Someone was raising hand. If you want to tell anything, just turn on your mic and tell. So E bar means electric field. I'm writing it for the first time. Again and again I will not write. E vector means electric field. Though we have studied it 2 minutes before. Electric field due to a point charge. What does point charge means? Point charge means the entire charge is at a single point. So let me just give you an example. If this is y axis, this is x axis, say there is a point here. Say an object is kept here and that particular object mass is m. Now this point for sure will have some x coordinate, some y coordinate, meaning it is here and here. So we'll have some x here and some y here. So these points coordinates are x and y and its mass is m. So this all of the mass is kept at this point only. So we will write it as point mass, meaning the entire mass is at a single point. We are humans. Are we point masses? No. We are extended bodies. Like if you draw a human here, it is this much big and this much wide. So the mass is in this region, right? So this is not a point mass. This is a point mass. The point. Same way we can have a point charge. The entire charge can be at a single point. In a wire, wire is not a point charge. The charges are there throughout the length of the wire, right? So wire is not a point charge. You can have a point charge like this. This is a point charge. Point charges are those we were studying previously, like this ones. Where did they go? Here. This is a point charge. This is a point charge. Okay. So we are going to write electric field due to a point charge, meaning you have a charge. It is here. It is kept here. And someone tells you, tell me the electric field at this point. This point's name is P, and this point is say r distance away from the charge, and the charge is q. This red dot is a point charge and you want to find the electric field here at point P. So you will just write electric field at point P is equal to 1 by 4 pi epsilon 0 charges value, which is q, divided by distance square. So this is the value of electric field, right, due to this point charge. Now we know electric field is a vector quantity, but we are neither writing a bar here nor we are writing some vector here, so it can give the direction. Why? Because this thing is scalar form. This thing is your scalar form. What happened? Who is raising hand? Theojax, what happened? Please tell me, or you can message me if you want. Thoyajaksh. How do you pronounce that? Thoyajaksh. Okay, so I don't know why Thoyajaksh is not telling anything. If you want, you can tell me in the chat, or you can just unmute yourself and answer. Okay, so this is scalar form, right? This force also, which we studied earlier, where did it go? It is here. This is also scalar form. You might have studied vector form also of Coulomb's law. Why this? So Ajax, what happened, bacha? Please tell me. I cannot see your message also. Somebody left. Okay, let me just continue. So this is scalar form. What is vector form then? Vector form, your class is till 6:30, right? People, hello, can somebody tell your class is till 6:30? As I am informed, your class is of 1 hour. If we start vector form, we will not be able to complete it. So it will get extended by a lot, and I cannot leave it in between. So I will not be starting with vector form. Instead, we will start with the vector form in some next class. Vector form we will do next class, wherein you can see vectors and all. So right now what we are going to do is we will tell that if this is a point charge, and as you go away from the point charge, your electric field is getting reduced. Mm, like we have people here. Okay. So if I plot the graph, this is your electric field, this is your distance. If you are very close to the charge, this R is less, right? You can see my cursor. Yes, you can see my cursor. If I press this thing, it becomes white. Okay. This R will be less when you are close to the charge, meaning the denominator is very less, meaning the value of E is more. Whenever the denominator is less, the numerator becomes big. So your E is high, meaning the R is here on the x axis and the E is high on the y axis. If you increase this R, if you increase this R, your E will come down, meaning somewhere here your E will be less. So your graph will look like this. It's not coming down. I don't know why. Because there isn't space on the tab. Okay, it is better now. So what you can write from here is E is inversely proportional to R square, and your graph is going to look like this. One more point, if there is some message, sir, you could please tell me the class timing. So as of today, as I am informed, it is from 6 to 7. I do not know the timing of the next classes. For today, it is like of 1 hour from 6 to 7. Like you have 4 minutes in hand. So I'm just discussing small things. So your electric field, you can say, is radially symmetric. This is the graph. One more point which you can say is your field is radially symmetric. Meaning, everybody just pay attention here. This is your charge, r distance above from this charge. We draw it here. R distance above from this charge, R distance below this charge, R distance towards right, R distance towards left. If you want to write the field here, at this point, at this point, at this point, and at this point, your distances are same. R, R, this is also R, this is also R. And you have a charge in between. Say the charge is capital Q. At every of these tick marks, these 4 tick marks, if you want to write the electric field, it is going to be the same only. K capital Q by R square. Now, if you want to write the electric field here also at distance R, if you want to write the field here, If you want to write the field here, anywhere on this circle of radius r, okay, anywhere on this circle of radius r, the field ka value is going to be the same only, which is this kq by r square. Also, like we are not face to face, if you have a charge in your hand, r distance in front of it, r distance in back of it, meaning you will have a sphere like this sphere. So this is in center, r distance above, r distance ahead, r distance back, r distance up, r distance round, r side, r. Imagine it, the charge to be at the center of the football. Inside the football, a charge is present, and on the surface of the football, on every point, your field is going to be same. So what you can write is electric field is radially symmetric. Your electric field is radially symmetric. E vector due to a point charge is radially symmetric. Meaning, on a sphere of radius r, the field ka value is going to be same only. I hope everybody is getting my point. Clear? Making sense? So on this sphere, what I have drawn, the field is going to be the same only, and the charge is at the center. If you draw a big circle, on this big circle, your field is going to be different. And if you draw another big circle, your field is going to be different. Next class, maybe the management, like the non-teaching staff, will inform you. Like today is Sunday, I think today is the demo class for you to get, like whatever I am teaching, you are getting it or not. I hope you are getting, like everybody gets what I teach. I teach here also. So maybe tomorrow or someday else is going to be your next class. The sir or ma'am, whoever is non-teaching, will inform you. So right now, what I want you to learn is electric field due to a point charge is radially symmetric. Meaning, if this is the charge, at r distance from this charge, your field will remain the same. I want these circles to be concentric. Concentric. I hope everybody understand what is concentric, meaning the same center. So these circles are now concentric. So on the inside circle, you will have some field ka value, and on the outside circle, you will have a slightly less value. Why? Because the radius of that circle is slightly big. So what we studied today is briefly about Coulomb's law. This is the entire scenario. You can zoom on your screen. This was the force ka part, first section, wherein we studied about dielectric constants and all. We saw that if you bring the charges in some medium, your forces gets reduced. And in the next part, we defined electric field. We learned how to write electric field. It is basically electric field is force over charge. You need to learn this thing. E is equals to F upon Q. And then we wrote the electric field due to a point charge. Here it is. And we told this graph will look like this, and we discussed what is going to be a point charge, like with an analogy of point mass. Then I told you vector form, I will teach you next class. And we saw electric field is radially symmetric. Mm, someone has raised hand. What is your name, Baba? Like you have just a dot over your name. What is your name? Khushi. Okay, Khushi. What happened, Khushi? Why you raised your hand, Khushi? Why electric field for positive charge is outward? So we'll discuss that. It is because if you take a positive charge here, this is your positive charge. If I draw a positive charge here, let me just zoom it. It's very big. This is a positive charge, and if you bring a test charge in front of it, test charge means this charge will only experience the force. It cannot exert some force. What will happen? This charge will go away. Who is joining at the end of the class? Okay. Okay, so Khushi, if this is a charge and a test charge is placed in front of it, this positive charge will repel the test charge. If you keep the test charge here, it will also repel. If you keep it above, it will also repel. If you keep it here, it will also repel. If you keep in front of it, like I cannot draw in front of it because we are on a 2D space. If the test charge is in front of it, it will come outward. If it is behind it, it will go backwards. So what is the meaning is, the behavior is that the charge, any test charge will move away. So that is why we tell the electric field is outwards. We will study electric field lines in very detail, for positive, for negative, for two charges, for charges of different shapes and all. So the basic idea is this: if there is a positive charge, that particular charge is going to repel a test charge. Test charge is always positive. So since the test charge will go away, we draw field lines pointing outwards. So this is it. We will stop for the day here, and next class onwards, please be interactive. Try to be in an environment wherein you can talk to me. Okay, like in a somewhere relatively quiet place in your home, and fix a place to attend classes. Always sit at that particular place as in you are in a physical classroom. Don't be on your bed, on your sofa while attending class. Fix a place while attending the class, and it will be helpful. So, like, you will get the environment of studying. Okay, so we'll stop here. Bye everyone, take care. We will meet in the next class. I hope you got everything what I thought. I will prepare a PDF of it and send it to you later. Okay, chalo, bye. You can leave.